Hi everybody, welcome to another section in Calculus 3, length of curve. So, this is pretty much like arc length in Calculus 2. Right. So what we're trying to find is the length of a curve, a part of the curve. Right. So, consider the parametrized curve given by this. By the way, there's a typo. We have three components, F, G, and H. So, this is not it. So, sorry. So it has three components. Derivatives are continuous and the curve travels once. So to go from A to B one time, from t equal to A, t equal to B only one time. Because if we find the arc length, if we go that two times, go around two times, the arc length will be twice as long, right? And the formula is given by this, of course. Let's see how does that relate to what we have in Calculus 2. So in Calculus 2, what we have, the arc length, if you remember, this would be great. If not, it doesn't matter. Let's say we want to find the length of the curve like this. It's difficult to find the length of the curve. So how about a straight line? So we cut the curve into a bunch of little segments. Let's say we consider this segment. This part of the curve is the length is close to the line. So let's call that is ds. And then we will have the x component. The reason we use dx and dy because that's a very small length. So we have ds square equal to dx square plus dy square. And we have ds equal to square root of dx square plus dy square. Next, we'll just integrate both sides. Integrate that give us s. Then dx square plus dy square. This is not precise proof, but at least it is kind of like a pseudo proof which help us understand things a lot better than just trying to remember the form. I will divide by dx square dx square, sorry. Since we divide by dx square, we multiply dx square, keep things balanced. And the dx square is still inside the square root. Now when we split dx square over dx square, just 1. And then we have dy over dx. Let's put the square like this. So what do we do with the dx square here? Move it on the outside. If we do that, it's just dx on the outside. So we have that. dy over dx, because that is derivative. So we have derivative 1 plus derivative respect to x square dx. And then we can go from a to b, whatever the limit is. Right, so that is Cal 2. Of course, later on we say instead of divide by dx square, we divide by dt square to have the same thing. Right, now what we have different here is it is only in 3 dimensions. So let's say that I will draw the box, a 3-dimensional rectangular box, very standard. Three-dimensional box. Pretty standard. And then I'm trying to find the length of the diagonal. I should have used ruler from the beginning. Anyway. So the diagonal from this vertex to this vertex. And let the length that be ds. So Pythagorean theorem for 3 dimensions, still the same thing. We have dx, dy, and dz. Actually, the left hand rule may not work, but let's see. let's be precise here and say x, y, and then z. Right, but still ds is equal square root of dx square plus dy square plus dz square. Right, so just like Pythagorean theorem. Now the proof is similar to here, but instead of divide by dx square, we divide by dt square. Again, it's not a proof, it's just like a pseudo proof. It's almost a proof. Again, if we want back to the s, we integrate. Don't worry about anything here, just like that. Now, if we want, we can divide by dt. If we divide, we have to multiply it back. Keep things balanced. dt right, because the x over dt is that's just derivative, and since we have the function x is equal to f of t, y is equal to g of t, we can replace with this formula. But I'm not going to even write like that. All I write here is square root. This I just say derivative x with respect to t square, derivative of y with respect to t square, derivative of z with respect to t square dt. We do go from t equal to a to t equal to b, so say a, b, right, like that. Of course, that is the magnitude of this. So out of the velocity or the tangent vector, so the length is equal to the integral of the magnitude of the tangent vector, or the magnitude of the velocity vector, or just the speed. I don't want to use the speed or velocity because sometimes t potentially can be negative. As opposed to in traditional sense, time cannot be negative. Right. Now, so in that case, like I said, I prefer to write in this form, a lot more compact than this or this. Right. Prove that the circumference of the circle radius a is 2 pi a. Now, if we use the arc length here in calculus 2 to try to prove that, this is very difficult. It's difficult to find the arc length using the equation with circle. Right. So remember, we did show that equation of, the arc length as for y equal to function of the function y is a function of x is given in this form. If we use this equation with circle, x squared plus y squared equal to a squared. So y equal to plus or minus square root of a squared minus x squared. The positive is the one above, the negative is the one below. Alright, if we use that function and take derivative square, put in this, so that's very complicated thing to do. Right? If we use this formula, it will be a little more complicated. So instead of do that, we write parametrized curve. So the circle of radius a is what we call the parametrized curve. By the way, I write parametrize or parameterize. Right? Either way works. Parameterized circle. Radius A. A cosine t. A sine t. And most importantly, the circle only one times. If we go more than one time, it will be more than one the length of an arc. So t 0 to 2 pi. Right. So that is parameterized circle of radius A. Assume we go one revolution only. Right. Then the formulas. Magnitudes of velocity vector. Magnitude of the tangent vector. So we'll find the tangent vector, derivative of that. Derivative of cosine is negative sine. So if A, negative A sine t, derivative is A cosine t. And then the magnitude. So that's one square, that's one square. So that gives us sine square and cosine square. Square, cosine square. Factor out the A square. Sine square and cosine square is 1. So we just have square root of A square. Now A is radius, should be, so just A. Remember, in general, absolute values of A, square root of A square is absolute values of A, which is A if A is positive or 0, and opposite to that if A is negative. Right. We know the radius is positive, so it's going to be just A. Right. And then the arc length is the integral of the magnitude of the tangent vector. We go from A to B, in this case 0 to 2 pi. Magnitude of the tangent vector is A. Of course, there's dt, right? dt. So we have at from 0 to 2 pi. Put in 2 pi and put in 0. So that just equals 2 pi A. So the proof for that is a lot easier than using this function and that formula. Right. Because we have the square root and integral, there's only a few functions that we can do. Next, we have find the length of complete hypocycloid. Not sure if we can do this yet, but let's just graph it. Actually, I graphed it earlier. Mode, make sure that is in the parametric form, and make sure that it is in radian mode. And then we type. Let's do that again. Cosine of t cube sine of t cube, and then graph. We might have to zoom in or zoom out, or even zoom. I zoom in already. I will zoom. Number 5 zoom square, so it will look a little better. So it looks like that. they look like a square, but if we want it to be a little better with Windows, let's go from 0 to 2 pi. I said here 0 to 2 pi, and 2 pi I divide by 100, so it will plot 100 point, so it will look like that. Let's see if we can zoom in a little. I choose zoom box. Much better. So that is now the namesake hypocycloid. Hypo usually is less. That's what I'm not sure if it's even true, but hyper is over, hypo is under, right? So if we have a square, says that. Okay. Now, actually, I'm not worried about that. Let's say if this is 1, what do we have? It's cosine sine. That is a circle or perfect circle, right? Now, if we have, let's say 5 or 3, it doesn't matter. It also the hypocycloids. It gets extremely closer to the x-axis, closer to the origin than the 3. But we have like 1 over 3. What we have is kind of close to the square, but actually I can call that hypercycloid. So perfectly, when the power is equal to 1, we have a circle. If the power is bigger than 1, is odd. The hypocycloid is inside, and hypercycloid is outside. So kind of like a square. So that's what the name is for. Right. Now, but we just find the length. Let's see if we can do it. Like I said, sometimes we won't be able to do this because the integral with the square root more often than not is complicated. But I will take derivative, find the magnitude. Derivative. Derivative of that. Let's just rewrite this as cosine of t cubed and sine of t cubed. So take derivative will be 3 cosine square, 3 cosine square, and the derivative of cosine is negative sine t. And then sine cube, 3 sine square, derivative of sine is cosine. Right, so that gives us negative 3 cosine square sine and then 3 sine square cosine, and then take the magnitude. That I prefer to just do this and then put in the integral and integrate. Right. That gives us 9 cosine square is cosine to the 4th sine square and 9. I said, I'm not sure if we can even do this. Sine to the 4th t cosine square. Right. It looks like we can do this though. 9. All of them have sine square and cosine square. We factor those out. Sine square, cosine square. Factor those out, we have cosine square left plus sine square. It's not that bad, which is 1, so that's convenient. Cosine square and sine square is 1, so we just have sine 9 sine square cosine square. Right? Now the interesting part. We did say that the magnitude have to be positive, right? Yeah. The length cannot be negative. But the square root cancel the sine square. It's not always positive. That is the problem. Where can I write this? Right. Remember, square root of a square is absolute values. It is the same if it's greater than or equal to 0. It is opposite if it's negative. So we have to take that into account. If t is in the second quadrant, then x and y and sine cosine may be positive, may be negative. That's why, in this case, if I want to find the arc length, instead of 5, the length of the whole thing, I find the length of one part multiplied by 4. So what I do is just multiply the length of one part and multiply by 4. So just find that length, multiply by 4. So I set this in when I teach Calc 2. Make sure when we integrate for the limit, always have to check. Have to check that. Let's say we go from 0 to, we only have one quadrant, so 0 to pi over 2, for example. Make sure that whatever the limit is actually the part that we're trying to find. So yes, from 0 to pi over 2, we have that part. Right. So why do we need that? Because in the first quadrant, sine, cosine are positive. So in that case, we can just get rid of the square root. Right. Now, the arc length is equal to, if we write from 0 to 2 pi, magnitude, or if we use 4 times, it will be just 0 to pi over 2. I'm going to write this. Right, so that will be 4. Yeah, 4 times the length. 0 to 2 pi, 0 pi over 2. Now for that one, both of them square root, both of them are positive. So we just say square root of 9 is 3, square root of sine square is sine, and square root of cosine square is cosine dt. Right, of course, here we can just use the substitution, or we use the trig identity double angle, that is. So sine double angle is 2 sine cosine. So in that case, sine A cosine A is sine of 2A divided by 2. Right, so that's what we have here. Sine 2 variables t over 2 dt. Right, we have 4 times 3 divided by 2. So that would be 12 divided by 2 is 6. Right. And then integral of sine 2t is negative cosine 2t divided by coefficient of t, 2, from 0 to pi over 2. Cancel out with the negatives. That gives us negative 3 cosine of 2t from 0 to pi over 2. Right, negative 3 cosine of 2 times pi over 2 minus a negative 3 cosine of 0, 2 times 0. Hate what this happened. Okay. Cosine pi is negative 1. Negative 1 times negative 3 is 3. Negative, so that is positive. Cosine of 0 is 1. So that plus 3. So it's 6. Right. So let's just make sure that it works. It's correct. Math number 9. From 0 to pi over 2. I forgot the 4, but that doesn't matter. Here we have, I just tried from the beginning. Anyway, no need to stretch. Sine square. It's 1.5. This is one part. We have 4 times that, 6. So that's good then. Alright, next, an eagle rises at the rate of 100 vertical feet per minute in the helical path, so kind of spiral like this, or spiral. How far does it travel in 10 minutes? So we just have that, take the derivative, magnitude, and then integrate. So the formula is in terms is rather simple, right? Just take derivative. Usually we have cosine and sine here because cosine square plus sine square is 1, so we end up something easy to do. If we don't have that, this could be complicated. Derivative of this, negative 250 sine t. 250 sine t is 250 cosine t. And then 100t derivative with respect to t is 100. And then find the magnitude. Again, we have cosine square and sine square. That's convenient. Right. Just a bunch of zeros. 250 square. 62,000. 62,500. Sine square. 62,500. Cosine square. 100 square, 10,000. And cosine square and sine square is 1. So just factor out 62,000. So we can skip that step, 62,500. we factor it out, right? And then sine square plus sine cosine square is 1, so we just have that. And that's just 72,500. Simple enough. And then we'll just integrate the length. In this case, we can say this is the speed. For travel 10 minutes. So in this case, t is measured in minutes. And to 10 minutes, so t will go from 0 to 10. The speed is constant though, so it doesn't matter if it goes from 0 to 10. It could be from anywhere in the interval of 10 minutes because the speed is constant. Right, so that's simple enough, and we just have 72 square root of 72,500. T from 0 to 10, put in 10, put in 0, put in 10, subtract 1, put in 0. So we just have square root of 72,500 times 10 square root. So I have about that much. Uh, 0.6. What is the unit? Right. Feet. So that is the distance the eagle travel. Right. Next, we have a little application. So it says, according to Kepler's first law, the planet revolves about the sun in elliptical path. Right. So the sun is not the center where the Earth travels around in the circular path. It actually travels in elliptical path where the sun is at one of the focus. So let me just Google something up real quick. Right. So, sorry. We have Kepler's first law. I usually just go to Wikipedia. Okay. Right. So, it says that the first law, the orbit of the planet is an ellipse, with the sun is as one of the two foci. Right. So it's no big deal. When we look at this, sorry, back to a note. What we have, those planets travel around the Earth. The minor axis and the major axis are almost identical. So even though it travels in an ellipse, but it is extremely close to a circle. What is not extremely close to a circle is something like the Halley comet. Let me search that real quick. Right. Now let's go to that Halley comet. Right. We know that the Halley comet going around a period is about 76 years. Right. So let's see. Right. The orbital period 75.32 years. Eccentricity, all of that. So we see the major axis is that much, but the minor axis is a lot smaller. So let's look at the diagram here. I think this is good. Right. So the sun is, okay, the sun is of course in the middle there. It's one of the focus. The inner one probably Mercury and Venus, and then the Earth is around this much. The Halley Comet will travel around in elliptical path, and we see it is a lot more elliptical. It is not like a circular path like the Earth and all other planets travel close to the circular path, but the Halley Comet, it is extremely that the Sun, so it travel around 75.32 years, and the Sun is one of the focus. So that essentially is the Kepler's first law, but we see the Halley Comet, so it's like that. So in general, we might have, so the Sun is at one of the foci. If we have something like the Halley Comet, it travel in elliptical path. By the way, if the period is 75 years, that means we only see it about 75 years. And it's very I'm really impressed that 300-400 years ago they actually can determine that it travel around 75 years. Because if you only see that once in your lifetime, difficult to track it. Anyway, so if it travel around elliptical path, it will come back. Now, if it travel around a parabolic path, we can only see it once. If it travel in the parabolic path, some comet actually travel in parabolic path or even in hyperbolic path. Those two we only see once, and then it will disappear. Anything in elliptical, it will come back. But like that. But we're talking about planet here, so it will certainly will have to travel around. So on most of this, like I said, the major axis and the minor axis are very close to each other, so they almost like a perfect circle. As you see, all of this, Neptune look like the ratio is kind of like a circle. Of course, when we have two foci and when it's too close to each other, the foci actually very close to the center. Right. By the way, the AU is the astronomical unit, and we see 1 is the major axis, so 1 is more likely from the center to the Earth, which is about that. Right, now we have that. Verify the length of the planetary orbit for the Earth. For the Earth, the length is about, I think, 6.28. Right. So we have that. So it's always take the derivative, then magnitude. Derivative of that is a cosine t. Derivative of a cosine t is negative a sine t. B sine t is b cosine t. Of course, a and b we can use those values later. But now let's take the magnitudes of that. Right. The problem here is a square and b square are different. We cannot just factor it out. Actually, those are very close to each other, so we can take something like average, something close to that, but not even do that. I'll just estimate, right? The question just, just estimate. So just put in the calculator. So the length is equal to, if we want one circular orbit, orbit travel one time from 0 to 2 pi, just the magnitude of the velocity vector, or the magnitude of the tangent vector. Just use that. By the way, those A and B extremely close to 1, right? If this is 1 and 1, the length is 2 pi, so this is actually 2 pi. So that looked very good there. A is 1 and B is 0.999, so I just put everything in calculator. I will store 1, store into A, and 0.999, store into B, and then just integrate math number 9 from 0 to 2 pi. We're still in radian mode. Yes. Square root a square sine square plus b square cosine square so yeah, that's about right. Yeah, so like I said, this is very close to a circle, so that's why it's not interesting. Something like the Halley comet is a lot more interesting. Yeah, anyway. Now, arc length in polar curve. Let f be a continuous, have a continuous derivative on the interval from alpha to beta. The arc length of the polar curve r equal to that. Now notice that in polar, this is regular r, this is not the vector r equal to this. So now the arc length is equal to that. So we actually can prove that relatively easy. So now, so we said just r and r prime. So proof. So first of all, we have r equal to, so that is the curve and theta between alpha and beta. This is the radius, not the vector r. Alright, so in polar, right? Polar, x equal to r cosine theta and y equal to r sine theta. Right? And then we do the same thing here. But instead of divide by something, we'll divide by some different things. So ds equal to square root of dx squared plus dy squared right. It just depends what we want to divide by. I will divide by d theta because r is a function of theta, x and y also a function of theta. Divide by that, multiply back by d theta square. Inside the square root, take it outside, we have derivative of x with respect to theta square, derivative of y with respect to theta square d theta. Integrate both sides, so I have s equal to integral of this. Right, now derivative. Even though I write like this, but r is a function of theta, so we cannot just write like that. Derivative of this, notice r is a function of theta, so derivative of x, I'm talking about x first. Derivative, that is the product rule, so r prime cosine theta plus r derivative of cosine is negative sine theta. So that is the derivative of x with respect to theta square plus for here r prime sine theta, and then r derivative of sine cosine. And then d theta. Right, just from alpha to beta, so pretty generic there. I do this a little bit differently. Usually I do the inside the square root first. Anyway, just keep it this form. Usually I just do everything and then put in the integral at the end. That will be a lot better than have to carry the square root. Hope that's long enough for that. Right, the inside we just square, so that gives us the derivative square cosine square, and then that r negative, so that becomes negative, so r square sine square away. So we have a minus b square, a square plus b square minus 2ab, a plus b square, a square plus b square plus 2ab. Yeah, if you multiply it out, combine like terms, that's what we have. So that's what we use. Multiply those two, negative 2 r prime sine and cosine. I have to write very small because I might not have enough space. Write that r prime sine square r square cosine square, and this is going to be plus. Yeah. So of course we have one like this, one like that. So this is plus in the middle, so we have two of them. 2 times r prime sine cosine d theta. That d theta, sorry. Now, plus minus cancel out, and then we can have derivative factor out cosine sine, cosine square plus sine square, and then we have r square and r square factored out sine square and cosine square. So put them together. R prime. Of course, r is a function of theta. Cosine square plus sine square. R square sine square plus cosine square. So that gives us alpha to beta and cosine square and sine square. So pretty much we just have the function r theta square and derivative square d theta. Right, so just like that. So the point here is O of the arc length. We start from the Pythagorean theorem and then divide by whatever we want to, and then multiply the same thing just to get to the formula that we want. Next, find and estimate the arc length of the spiral on that. So we have the function which is second derivative of that is going to be 1. So the problem becomes the arc length is equal to from 0 to 2 pi square root of the function square plus derivative the function theta square derivative is 1, square still 1, right? Right. Now if we do that by hand, it requires the integration by parts, trigonometric substitution. There are quite a few things here. So pretty much the whole chapter in calculus 2 in order to do that. So we're not going to do that, we just estimate from 0 to 2 pi square root of 1 plus some variable square. So about that much. I just an estimate. So the spiral from 0 to 2 pi is that much. Just an estimate. Next, I'll find the arc length of the circle r equal to 3 cosine. What does that look like? Now this is in parametric. I need in polar. 3 cosine theta. Let's zoom out. So about that. By the way, if this is 0, this is 3, the radius is 1.5. We have the radius, we can find the arc length relatively easy, right? But I just want to use the formula there. So in polar form for r, take derivative. And now the limit here is interesting. What will be the limit? Remember, whatever we set the limit, make sure that we go it 1 times around the curve. Right, so don't say anything, right? Now, we recommend that we go here and hit enter 1, 2, 3 times. Oh wait. What I want is the one that have a dash and a circle. Right, let's see the graph. See. So actually it's go over the circle twice. Right? So in that case, have to change the limit. How about go from 0 to pi only? Yes, it go around the circle 1 time. So the limit here is from 0 to pi if we set up the limit. So where there's parametric or polar, and when we find the arc length area, whatever it is, when we set up the limit, always graph it first and put in the limit to see that actually the part of the graph that we want to. Otherwise, it could be tricky. Here we only go from 0 to pi though. We just have r square plus derivative square. Both of them are function of theta. So we just have 0 to pi. So 3 cosine theta. 3 sine. Three square that will give us 9 cosine square. Negative 3 square is 9 sine square. Cosine square plus sine square is 1. So we just have 9. right? It's web 9, 3, so have 0 pi, so 3 theta from 0 to pi, so this is 3 pi. I did mention that earlier. The radius is 1.5. The circumference we did prove earlier, 2 pi times the radius, 1.5, give us 3 pi. Right. Yeah. So it is in the polar form, it's a little bit different, but in parametric form, just take the magnitude, just take the velocity vector, take the magnitude, integrate. That's pretty much it. Arc length as a function of parameters. So we can write the function as a, the vector value function in terms of t. Now we can do that, and we say if the magnitudes of, if the speed is equal to 1, then the parameter t corresponding to the arc length. So, do we have any of that? Actually, no, we haven't done anything where the speed equal to 1. So, no. Right. So, what we focus here is the arc length as a function. So, and here we say, if we form the function where the function is in terms of t, which is the upper limit, and a is where we start. So, pretty straightforward, right? We still find the velocity or take the derivative and then find the magnitude. So, here we take the derivative, -2 sine, 2 cosine, and then 4. And then the magnitude. Four sine square, 4 cosine square, and 16. So sine square plus cosine square is 1 factor of the 4, so we have just 4 and then 16, which is square root of 20. Now, if this is something that have t in it, then we have to do something else. But here, when we find the arc length function, instead we go from 0 to something, we go from 0 to t. By the way, I should not write L, just write S of t. And then we just have square root of 20. If we have t in here, we have to change something else to u. So if we have t here, change that to u. But this is just a constant, so it doesn't do much. Put in t, put in 0, and so we just have square root of 20. T. What it does is, let's say we have this function. And remember the problem with the eagle. If we can have something like this, and then I say, what is the arc length when t equal to 10 minutes after it? We just put 10 in here, and we find it. Right? As earlier, we find for the problem with the eagle flying. This is the arc length times t. That's the arc length function. Put 10 in that, we find the length. Right. So, that's all we have. So I'm going to I stop here for this section. See you in another video in Calculus 3. As always, thank you for watching.